We present Dodica Fusion, a compact, multi-model fusion framework for tracking a pen-shaped device using only a single camera and an embedded IMU. Traditional systems that rely purely on vision to estimate the pen tip position are often not robust, especially in low light when the marker is partially occluded. In our visualization, these camera-only estimates are shown as purple dots. In contrast, the fusion models lean more on the IMU in low light settings, which make the tracking much more stable. Those fused estimates are shown as red dots. Our hardware has two main parts. First, a dodecahedron marker provides rich visual feature for the camera to track. Second, an embedded IMU inside the pen captures high rate acceleration and angular velocity data. Together, they give us a complementary information about the motion of the pen. The IMU used in this research is Xiao NRF52840 Sense by Seed Studio, and the camera we used is Logitech C270 webcam. Any other 6-axis IMU and cameras should also work, but IMU will require additional modification to the provided code. On the algorithm side, our fusion model uses an extended Kalman filter, known as EKF, to estimate a 22-dimensional state, combining both vision measurements and IMU signals. The goal here is to recover the virtual pen tip positions in a camera coordinate system. Because our motion and measurements are nonlinear, and because the camera doesn't update every frame, a standard Kalman filter would not work here. Thus, we choose extended Kalman filter. In the prediction step, the EKF integrates IMU gyroscope and accelerometer measurements to propagate the 22-dimensional state forward in time, updating orientation via quaternion integration and updating velocity position using acceleration minus the estimated IMU bias. In the update step, the camera provides an absolute pose measurement of the dodecahedron marker, and the EKF computes an Kalman gain to compute the predicted state, aligning orientation and position to the camera frame and reducing accumulated drift in both motion state and IMU bias term. At a high level, the filter works in two steps. First, it predicts the future motion of the pen using the history of camera poses and IMU readings. Then, when new camera or IMU data arrives, it corrects that prediction to keep the estimate consistent with the latest measurement. It is essential to understand the coordinate systems used in this framework. On the left, the head coordinate system aligns with the camera coordinate system, which serves as our primary reference frame. In addition, we define coordinate systems for the pen, the tablet, and the world. When we zoom into the dodecahedron, we see that each face has its own local coordinate system, and each Aruku marker corner also carries its own local frame. For consistency and simplicity, all of those coordinate systems are ultimately transformed into camera coordinate system to further output the estimated pen tip position. Here you can see the system running in real time. On the left, the green bounding boxes show the camera detecting Charuku markers on the dodecahedron. On the right, you see the corresponding 3D pen tip trajectory being updated as the pen moves. The IMU runs at about 145 Hz, providing very frequent updates, while the camera poses arrive at around 30 Hz with occasional delays or dropped frames. This mismatch in frequency and latency is one of the key challenges that our future model is designed to handle.